In this video, we're going to go over the multivariate chain rule in analysis, and we're going to go over a rough sketch for a proof for anyone doing, I think it's calculus 2 or 3 analysis of multivariate functions. Before getting into the main meat of the video, I'm first going to go over the use of the definition of the partial derivative I'm going to be using in this video. It's very important to look at whatever you're using in your field or whatever you're going to be using derivatives, because it does vary a lot, and you do have to be really careful when using it because it does suffer from a lot of abusive notation, unfortunately. But it does, luckily, at least in this video, and I assume among math people, I don't know about you physics people, it does have a very specific definition, an unambiguous definition, and it's right here. So if you have a function that takes an n inputs, so x1 to xn over here, and you want the partial derivative is essentially what is the rate of change of a function when you only change one input. How does the function change when you change one input of the function specifically, and the rest are held constant, and it's going to be evaluated at whatever the rest are held at, and it can be denoted in mainly two ways. So you have day xi over here, or you have capital D sub I. From experience, D sub I, the capital D sub I, is a lot less ambiguous because you're saying, I want this specifically, this entry into the function, whereas xi, this derivative with respect to, partial derivative with respect to xi, it depends on whatever notation you're using to denote each of the entries into f. For example, if f was taking functions, hint hint, g1 up to gn, then you can denote the ith partial derivative of f by day gi of f, and this will probably become a lot easier to use, a lot more easy to read when in some areas. And it just so happens to be this limit over here, which is the familiar difference quotient, except everything else other than everything but x sub I, the ith entry, is actually changing and being divided by the difference over here. Before jumping into the higher dimensional cases, let's first consider the one-dimensional case, just to get our foot on the pedal. Really, it just simplifies to the regular chain rule. And here's an important fact, something that I'll use pretty often. I'll use these symbols interchangeably. The partial derivative, by the definition, note that this might differ if you, for example, go into physics where these have different meanings. Partial derivative with respect to the only component in a single dimensional function, f of t, I think it's called univariate or whatever, is exactly equal to the total derivative with respect to t of f evaluated the same component, because there is only one component, and the definitions happen to just align. The limits happen to align. Now we dive into the weeds of the higher dimensional case, except now we're just going to first consider a simple case. The simple case is already broad enough. It has a lot of applications. But soon we're going to get into a more complicated case. The reason it's called simple is because the vector function that we're composing with f, g over here, so hence chain rule, only maps from r to r to the n. Generally it can map from r to the k to r to the n, and then composed with f, which maps from r to the n to r. F is a scalar field over r to the n, and g currently is just a vector field over r. Let's hop into basically an exploration of how we would prove this chain rule for the higher dimensional simple case. Let's start with first principles. Derivative with respect to t of f composed with g of t. And note that this simply denotes plugging every component, g1 up to gn of t, into f as an argument. We expand this, and then first principles. Currently we haven't done anything really innovative. This is the problem, this is where we get stopped. This is why we can't directly find it. Where do we go from here? Well, first, what we want to do is turn this into partial derivatives. We're going to make the assumption, a very important assumption, that the derivative with respect to t of every gi exists, and the partial with respect to xi of f exists for all I, for every element, every input into the function. Now what we don't want to do is turn this into a bunch of partial derivatives or derivatives of this much more easy to find g sub I. How will we do that? Let's first try, what we want to do is somehow add 0 or whatever into this limit so that we eventually get a bunch of different functions where the only differences, the only subtractions we're doing, difference quotients, is the difference between a single component of the function f. Well, let's try and do that. I'm going to show you the function, or show you the first step, and then explain. Let me erase this to make space. Let's look at what we have here. So what we have is the original functions here on the left and on the right. And now I'm adding 0. I'm adding this function here, f, where we only evaluate g1 at t0, not that t0 is approaching t, but we hold everything else. So we're only varying the very first component, but not exactly, because we're not actually plugging in t and t0 into the first component. We're plugging it into a function, just plugging it into f. So it's sort of trapped inside this function, so we can't really jump straight to a partial derivative from here, but we can work towards it. And this junk on the right, let's just ignore it for now. You'll see later that it really all just simplifies very nicely. We split this using limit rules. Of course, every limit rule that you see, that you might learn in analysis, it's only valid if we know that the function exists. It would be really boring if this didn't exist and we couldn't do all this, so let's just assume that it does. This is really hand wavy. You can solidify this in a proof with epsilons, deltas, theorems, whatever. But really, this is just to get a grip of rough understanding of the proof. We split it into this. There, we get what we want. We're varying the very first component on this left-hand side, and we're leaving everything else constant. That smells of partial derivative. But we're not there exactly because we don't have the full definition. We're not actually dividing by the difference of the first component here. We're dividing by the input into the function of the first component. So let's analyze this even further. Let's look at the limit. And I did give a bit of a spoiler here. We're going to multiply by this, by 1 on the right here. You have to be careful because sometimes g1 might be a function such that even if t and t0 differ, g1 of t and g1 of t0 equal. And no matter what, there might be a lot of different functions. No matter how close t0 gets to t, it might still equal 0. But there are ways to work around this. There's a really formal proof on Wikipedia. So let's just ignore that for now. The reason I'm doing this is because now if we look at the denominator here and the numerator here, what we have is we're varying the first component in the numerator, g1 of t, g1 of t0. These differ, and they're getting arbitrarily close because note that since the derivative of g1 exists, it's continuous, hence as t0 approaches t, g1 of t0 approaches g1 of t. And we're taking the difference of the first components, and everything else is being held constant. So very nicely, we do in fact get a partial derivative from that of the first component evaluated at g of t. And then what do we do with the other numerator and denominator? We get g1 of t minus g1 of t0 divided by t minus t0. That is straight up just the derivative of g1, which is nice. Now we have the derivative of g1 and the partial of f. This is exactly what we need. So I'll put it down here. This limit here, where we take the top we take the numerator and denominator, turns out to just be the derivative of g1 with respect to t, evaluated at t. And then, oh, here I made a bit of a mistake. This limit over here is going to be the derivative of f. So note that we're not actually taking the limit as, say, the first component approaches, gets close, arbitrarily close. I'm dividing, we're taking that difference quotient, but it does turn out, since G1 is continuous, you can prove that it is indeed exactly equal to just the partial derivative of the first component when varying the first component. So we do indeed get the partial derivative of the first component of f. I note I made a mistake here. It's going to be g of t. And now let's further our investigation into the proof of the higher dimensional case, the simple one. We deduced this from the previous slide, from first principles. It just breaks down to these two limits here. The first one just varies the first component. We have the partial derivative with respect to first component of f, and then this junk in the back that I said would simplify later on. We deduced from before that the left limit here in the sum deduces to just the partial of f with respect to g1 evaluated at g of t, that is, I make this mistake very frequently, times derivative with respect to g1 of g1 with respect to t. Note that this right hand side is just purely a function of t that outputs in one dimension. So we have is partial of f with respect to g1, and here is that use of notation, g vector evaluated at this vector times dg1 dt. This is the very first part, what will be a sum, and that just goes over here, and now we have this junk over here. How do we simplify this? Well, we do exactly as we do before. We add 0. Let me erase this over here. We're only varying the second component. So the first component is held constant at t0. Everything else, apart from 2, is held constant at t. Ooh, I highlighted the wrong one. You're held at t1. Everything else is held at t. Only thing that changes is this g2, which is evaluated at t here, minus t0 over here. And we're dividing by t minus t0. We follow the exact same process as we did before, and because, note that the first component is not being held at the same variable as every other thing. It's only being held at t0, where everything else is being held at t. But note that since t0 approaches t, and we're not varying the first component, nothing fishy is going on, and it's continuous, and f is nice. It doesn't make a difference. It ends up evaluating to the same thing. And so following the exact same process as before, we end up with this here now. We get the partial of f with respect to g2 times derivative of g2 with respect to t. And here the partial with respect to f of f with respect to g2 is evaluated at g of t, that vector. And then we get this chunk over here. And then we just continue this. You can see there's a pattern emerging. And you can probably fish out this pattern by seeing that this partial g2, if these refractions would cancel out with this derivative g2, and this just continues to go on, and we get this sum over here. This is formally the higher dimensional simple case, where f maps from r to the n to r, and g maps from r to r to the n. The derivative on the left hand side is in fact equal to this sum, where every element of the sum is of the form derivative of f with respect to the ith component times the derivative of the ith function of g with respect to t. The partial of f is evaluated at g of t, and the derivative of g is just evaluated at t. Now that we've completed our exploration into finding the formula for the simple higher dimensional case, I'm going to state it outright just to summarize things. So we're going to first define g over here and f over here. G is a scalar function, g is a vector function, that maps a scalar to a vector, and f is a scalar function, vector to scalar. And what we're going to do is try to find out what the derivative of their composition is when you evaluate it at t. And note that this is a bit of a notation, a bit of a hand-wavy notation. What we're saying is that we're first evaluating g at t, and then we're plugging each of these entries. So what happens is you get an n-dimensional vector. We're taking this vector and we're plugging it into f as the entries of f. We're making the assumption that n is greater than 1, however it can indeed be equal to 1, as we'll see, because the formula simply collapses to the regular chain rule that we are familiar with. First we have to make two assumptions. The first is that the partial at every component of f, for any vector that you plug into f, any n-dimensional vector, exists. And here the domain of f has to at least be an open subset of R to the n, so that limits are defined. So f maps from some open subset of R to the n. Very quick handwriting. I'm using a mouse, by the way. And here derivative with respect to t of g sub I exists as well. For every I, 1 up to n. Once these are satisfied, we get this formula over here. Derivative with respect to t of g of f composed with g is this gnarly sum over here, where, please note, I did overlook this, the partial with respect to g sub I of f is evaluated at the vector, at the function evaluated at t, and this is multiplied by derivative with respect to t of g sub I. Probably denote that a bit more clearly. Of g sub I, like that, evaluated at t. And this is every element of the sum over here. And the reason I say it collapses is because when n equals 1, suppose n equals 1, what do we get? We get that the only partial derivative of f is the partial derivative to the first and only component. So we get derivative of f with respect to g1, or since there's only one, I'll just refer to it as g. And since this is a partial derivative of a scalar input, scalar output function, it is exactly equal to just the regular derivative. So let me use that instead. We get df dg, which is the first part, which we like, and this is evaluated at g of t. First part of that very familiar chain rule, multiplied by derivative of the only function with respect to t, dg with respect to t, evaluated at t, or just f dash g of t times g dash of t, the regular formula that you're familiar with. As hinted before, the generalized case, the main difference between this and the simplified case is that the domain of g, the input into f that we're composing, has now a vector input and a vector output. The dimensions differ. So let's recall the definitions of g and f, and we're going to now just include the more general definition of g. We're not going to consider a vector output for f, we're only going to consider a scalar output. If you want that, that's going to be way beyond what I can do, includes Euler Jacobians. I suggest you just look at the Wikipedia page or some other helpful YouTube videos. So basically, R to the, we're mapping G from a vector space in R to another vector space in R, from the range of G to a scalar, and we're going to analyze the composition of f composed with G, or the function f composed with G, evaluated at now is going to be a vector t, u, whatever, and we're going to have k of these inputs instead of just the single input t. And I could denote these by like t1, t2, but just for brevity, because I'm only going to consider the partial with respect to one of these, I'm just going to refer to that as t, and if I ever need to call on more of these inputs just to prove a point, I will name them letters. That is just notation I will try to stick to because it just cleans things up very nicely. Let's recall the simple case, the simple formula for the multivariate chain rule. over here, instead of the regular derivative ddt, that is what I used in the previous slide, I'm going to use just the partial, because that's how we're going to expand into the generalized multivariate derivative. Note that we don't consider the total derivative of the whole input. That is way more complicated. What we have is the partial with respect to t of f composed with g is this gnarly sum over here. What changes between this and the more general multivariate cases? Absolutely nothing at all, except the fact that this dg dt becomes a partial instead, and it's going to be evaluated at t, u, v, whatever inputs you're putting into this composed function. And this is very neat, and please note that we are taking a partial with respect to one of the inputs into G, not like the entire vector going into G. And the very neat thing is that there's a scent of recursiveness in this. What we have is that we want to find, when we're finding the partial with respect to t, f of g of all these inputs, we need to find the partial with respect to t of g of a bunch of inputs. And this is recursive because these inputs can also be functions. These can be functions of t, and say, imagine if we're taking respect to x, and these are all functions of x. Then we're going to need to reapply the chain rule, and this is very analogous to reapplying the chain rule when we have these nested functions in single variable calculus. Continuing on with our pursuit into this generalized derivative, let's consider an example. Here we want to find the derivative with respect to t, this should be a partial with respect to t, sorry, of this function over here. And we don't really care about the specifics of the function or the functions going into f. We only really care about the overall structure. If we put in a sine or cosine, more strict functions, this really just overcomplicates things. And here I'm going to assume, at least, this is what I denote. When these inputs into G don't have an explicit dependence on any variables, they're just going to be constants. They're not going to be, they could be functions, but they're going to be functions at most of variables not included in any of these inputs, not included in any of the inputs of G. And you may notice that in the previous definition, we strictly required that every function of G has the same number of inputs and the exact same inputs. Here we don't have that luxury. However, note that that really doesn't change the overall formula. The exact same formula can be applied for a reason that will be explained later. So as you can see, we're just going to apply this sum. And what is the sum? And if you make the exact same mistake, this should be a partial. What happens? Well, we're first going to look at the sum. We're going to expand the sum. It's going to be partial with respect to g1 of t, partial with respect to g2 of t, and partial with respect to g3 of t. And note my assumption, none of these variables depend on anything else if not explicitly stated. So x, y, and z, they don't depend on t. So the partial with respect to g3 of t is 0. G3 has no dependence on t. So this part over here vanishes, whereas g2 and g1, they do. So we cannot exactly simplify them any further. So this whole thing completely simplifies to just this sum over here. Partial of f1 with respect to g1 times partial of g1 with respect to t, and you can read the rest. It's just this sum of two elements. Let's look at now another case, and this is going to elaborate on that recursiveness that I talked about in the previous slide. We're looking now at the partial with respect to t of exactly the same function as before, except now y has a dependence on t and u. T is thrown in randomly. It isn't going to make any changes to the calculation, but let's just see how things roll. So now we're going to again look at the gosh, I make so many of these mistakes. We're going to expand the sum. We're going to get day g1, day t, that doesn't change, and neither does g with respect to t, g2 with respect to t. Now we have g3 with respect to t. This does change, because it does indeed depend on t through y. So we're going to have to now reapply the chain rule. We look at the derivative with respect to t, the partial with respect to t of g3, where g3 is this blah blah blah, is going to expand into this. This should be a partial. Derivative with respect to x, the derivative of x with respect to t just vanishes because it has no dependence by that assumption. Neither does z. But what about y? Y does have a dependence, and it's a very simple dependence. It just relies on t, not on u. Hence, we're going to skip a few of the even further recursions and just jump straight to the point. This is equal to day g3 day y times day y day t. We're going to sub that back into this formula, and we're going to get basically these two are exactly the same as the two from above, but this one over here is now going to be this day f day g3 times now this one over here, day g3 day t, which expands into this one over here. As we've seen from before, there is, in the second example, a lot of recursive application of the chain rule in the multivariate chain rule in that problem, and it seems a bit overkill. We're just trying to find the structure of a function, and this chain rule method, at least this recursive application, seems very algorithmic, seems very mechanical and easy to perhaps simulate or do more efficiently. And there is indeed a method of doing this, and it relies on visualizing. It's very visual. It visualizes the structure of the function and its dependencies, and then determining from that the chain rule, because that's all really the chain rule cares about to be used. So let's look back at the example. We have the partial with respect to t of a function f, and f takes in g1, g2, and g3. G1 takes in these two variables, G2 takes in these two variables, G3, it's not so trivial, it has two variables, and then another function, which takes in two more variables. Let's try, the way you would visualize this with a tree is, first, you start with the root node, which is going to be f, the main encompassing function. Then you'd say that f depends on three things. These things are the largest encompassing, essentially, function that is being parsed in. You're putting the entire function that is going into that input, into that element in the vector, essentially, a vector input into f, and you're just shoving it into that place. So what's f taking is taking g1, g2, g3. This is basically the thing that's going into f. And then what is g1 doing? We have to now draw the tree for g1, g2, and g3. g1, it takes t and u. For g1, we terminate here because we end at variables. g2, it takes in two variables as well, v and t. And g3, it takes three variables, x, y, and z. Except y is a bit special because it's also a function, hence we just continue down on y to t and u. And the way you'd use this method is, I will just show it now. It relies on a lot of properties of the chain rule, some very nice things that allow us to do this, just make this work. So what we do is we start at the root node f, and what we would need to do is find every path down to every instance of the variable we care about, or t, which is t in this case. I will show an example for one of this, and what this entails about the structure of the chain rule. So let's do one path. We're going to go from f to g to t. We go from f to g and then to t. What does this entail? This entails one term of the sum of the chain rule. If you recall that the chain rule is basically a sum of these terms. And what is this term going to look like? It's going to look like, essentially, the product of the partials of essentially what we get from each of these steps. So the first term of the product is going to be day f day g1. The second term of the product is going to be day g1 day t. Because we can see f to g1 entails day f day g1 day t, because t follows g1. And then you could be very strict. You could say, oh, well, you could do day t. However, that's just one, and you can do this indefinitely. So really, we just stop there. We stop f to g1 and g1 to t. And this is going to be the first product of the chain rule. And that's put right there. And what's the next step going to be? It's going to be basically exhaustively finding all of these paths to t, and then adding them up. And because addition is commutative, you can do these in whatever order you like. There is no necessary order. So next one we would do from f to g1 to t. From here you'd get day f, day g2, which is going to be the first term of this product. The next one is going to be day g2 day t. Simple enough, and that's the next term of the sum. The third one is going to be from f to g2 to g3, f to g3, from g3 to y, and then from y to t. I could probably visualize this a little better just by circling this path over here. What does this path entail about our product? It's going to be basically the same process as before. We're going to do day f, day g3, times this next step here from g3 to y is going to tell us to do day g3, day y. Next step is going to be y to t, so it's going to be another term, day y, day t. And that's going to be the third term of our sum. And there is something important to note here. It's going to be that these are all functions, hence they expect inputs to actually have a concrete value, and they all actually require distinct inputs. That is important to note. So in this very first, so these are all, each part of this sum requires distinct inputs, or at least they're not necessarily going to be the same. In the first one, in f, you're going to input whatever f had going into it. So this function g1, g2, g3 of these variables t, u, v, t, x, y, and z. Into g1, a similar vein to f, you're going to input whatever was going into g1 originally, so just whatever t and u were, and then so on for the rest of these. So wherever you see day f, it's going to be whatever went into f, you're going to put in this partial. That's what you need to evaluate this. Whatever into g2 is g2 or g3, whatever was going into g2 or g3 respectively. And then with y as well, you're going to have whatever is going into y, i.e. t and u, you're going to plug it into day y, day t. And then you put these in, and then you would evaluate the full chain rule. After the previous example, I'm just going to move on, use it for one more slightly more complicated function with a perhaps strange edge case that you might run into. Here we have derivative with respect to x partially of f of these three functions here. We have g1, g2, g3. And as we can see, g1 has a function that depends on x, so g1 does indeed depend on x somehow. g2 does not depend on x, so we do not really need to consider it in the graphical representation of the dependencies of f with respect to x. In g3, it has now two references to x in its definition. It has an input of x and a function y which depends on x as well. So it has now two dependencies on x, and this might change calculations a little bit in a way that you do not expect. Excuse me. Or at least in a way that can be simplified when you run through the calculations. So first let's draw the dependencies of f with respect to x. So we have
depends on G1, G2, G3. G1 depends on T and U. U depends on X and V. G2, we do not really need to consider it because we're going to be drawing paths to basically X's in this graph. And since G2 does not depend on X, it's not going to have any paths going through it, so we may as well just exclude it. G3, it depends on X itself, depends on Y, which is a function that depends on X, and Z, which we may as well include. Y depends on TU and X, TU and X. Now let's draw the partial derivative. Let's determine the partial derivative, from this graph. The first path is going to be F to G to U to X. Let's see what that comes out to. So we have F to G1, day F, day G1, and this is going to take the inputs of whatever F was already taking. So in this case, G1, G2, G3 evaluated all those many variables, and I'm going to exclude that just to simplify things, just to clean up the expression. We're going to have G1 to U, that's going to be day G1, day U. And what input is this function going to take? It's going to take, basically in similar vein to F, it's going to take whatever G1 was taking, so T, and then U, which U takes X and V. Let's keep going, U to X. So U, day X. So this is the last path from U to X. That gives us day U, day X. And this is going to take whatever U is taking, which is X and V. And interestingly, we could indeed, if we think of X as an identity function, as in a function where it's just defined to be X, we can multiply again, because X now depends on X, which depends on X. But we're going to take derivatives with respect to X of X, which is just going to evaluate to 1. So we might as well just end here. And I'm going to state this for G3. Now let's look at G3. So the second path is going to be from F to G3, G3 to X, or to Y, and from Y to X. Now what do we have here? So we're going to add a sum, and you could do this in two different ways. First, you can see it has two distinct branches. As an F to G3 to X, you add on whatever comes from there, and then F to G3 to Y to X, and then you add on whatever comes out from there, which is going to be slightly longer. Or you can simplify things by seeing that you're going to have a product of day F, day G3 automatically from both of these elements that we're adding. So we may as well just factor that out preemptively. So we're going to get day F, day G3. And there's some other reasons you can do this. You could probably explore this when looking at the actual formula for the multivariate chain rule. This is going to multiply by the sum of every branch from G3 to X now. So it's as if we're reducing the problem of day F, day G3 down to just day G3, day X, every single branch that goes there. So the first one is going to be this first branch on the left here. I'm going to highlight that in dark blue, if you believe that that's dark blue. Day G3, day X, and that's going to be all. And note that this is going to take in the input of whatever G3 is taking, so X, Y, and Z. And then we're going to add on day G3, day Y, the second branch. Times day Y, day X. And there is a very important distinction to make here. Some notational messes that come from our use of notation, which is why I'm going to rewrite this one to be a little more specific. This isn't day G3, day F anymore. It's going to be the partial of G3 with respect to its very first component specifically, not with respect to X. So let me clear things up with this D1 G3, because we're not taking the derivative of G3, the partial of G3 with respect to every element. rather how it changes when we change just not every mention of x, but rather just when changing the very first parameter, which just so happens to be x, which might be a bit confusing. Because it does indeed, if you take the partial of g3 with respect to x, so the partial of g3 is equal to this thing over here, this whole mess over here. And so it might be a bit confusing when in this mess you have day g3, day x, because of this first branch. So we're going to be a bit more specific and say specifically derivative of the first component of g3, the partial derivative. And this is going to be evaluated, whatever g3 is evaluated at already. And then we're going to do the same for y, but we don't have any ambiguity in y, so we're just going to go day g3, day y, day x. That's a very important thing to note. Sometimes it might be ambiguous what you mean by the partial with respect to x. And the actual, like, whatever x corresponds to, the partial of a component. Because, strictly speaking, this doesn't really make sense, this partial with respect to x, if you consider f as a function of these three functions, as a function that takes in these three functions as input. And these functions, they take in different inputs. There is no clean f composed with some vector, unless you somehow extend the definition of this function up here, the one that we're considering, so that we can transform it into this much neater. So, for example, it's going to be a function of t xv. We have v, we have t, we have x again, we have y, which is a function of tu. So I'm just going through the inputs, and then z. Then this partial makes sense. So really, please make note of all this hand wavy notation. That's probably the biggest hurdle you're going to go through when looking at these partial derivatives. But that is going to be the actual answer for the partial derivative with respect to x, in the sense that we're changing x, every instance of x in f over here. So let me clean things up. And yeah, that is the answer to the last question, and that's the end of this video.